All right, in today's lesson here, we're going to be looking at the idea of logarithmic differentiation. So logarithmic differentiation, essentially when you want to take the derivative of a given function like this one here, to take the derivative directly, i.e. like if I were to go ahead and just take y prime here, this would involve the quotient rule, and then within that you'd have the product rule, chain rule multiple times, can be very messy. So a cleaner way of tackling this problem is using the idea of logarithmic differentiation. So what you do is you take the log of both sides. You can use any log you want, any base you want for the log, but typically a base of e is used, so that would be your ln. So I'm going to take the ln of both sides of the equation. So by taking the ln of both sides of the equation, I end up getting this expression here. And now the advantage to this is we can use our logarithmic properties. So now I have the ln of y equals the log of a over b. I can write this as my log a minus the log of b. Then I can continue this here. This becomes ln of y. You can use your exponent rule. I can drop this down. This becomes 5 ln of x. And once again here I have the log of the product of two expressions. I can rewrite that as the ln of 1 minus 10x plus the ln of the square root of x squared plus 2. And you can see here you can make this expression appear more linear by applying your logarithmic properties. And we still have more logarithmic properties. I have the ln of y equals 5 ln x minus the ln of 1 minus 10x. Again, here, this is to the power of a half, or at least I can drop down the half. And now we have this expression. So now, by taking the ln of both sides, I've now re-expressed this in the following form. So now I'm going to take the derivative of this with respect to x. You kind of have to watch out here. When I take the derivative with respect to x, if I assume this is with respect to x, which is not, it's just going to be 1 over y. But again, that was not with respect to x, that was with respect to y. So I have to apply the chain rule and take the derivative of the inside. And because I don't know what y is, I'm going to write this as dy dx. So here, this is your implicit differentiation portion. I've taken the derivative of this expression as if it was with respect to x. So in this case, the derivative of ln x is 1 over x, so derivative of ln y is 1 over y. But this was not with respect to x, with respect to y. So again, by applying the chain rule, you have to take the derivative of dy dx here. So this is going to equal. Now if I take the derivative with respect to x, this is with respect to x, we're all set. It's going to be 1 over x minus, this is going to be 1 over 1 minus 10x. And again, this was not just an x, it was a 1 minus 10x. So I have to take the derivative of the inside, which is negative 10. Minus 1 half, and again the derivative of this will be 1 over x squared plus 2, and again this is not just an x, it's an x squared plus 2, so the derivative of the chain rule, you get 2x. So here I get 1 over y times dy dx is equal to 5 over x plus 10 over 1 minus 10x minus x over x squared plus 2. And last step here is you're looking to isolate, like I want dy dx, that's my y prime. So therefore y prime is equal to y times 5 over x plus 10 over 1 minus 10x minus x over x squared plus 2. And to finish this off here, my y prime, which is what I'm interested in, is equal to y. Well, we know what y is. Y is this whole expression right here. This is my y. So let's pop that in here. That's my y value. And then you're multiplying by this expression here. So therefore, y prime is equal to my function out here, the y value, times 5 over x plus 10 over 1 minus 10x minus x over x squared plus 2. And we have our derivative much cleaner using logarithmic differentiation. Let's take a look at some more examples. So the next example here, same idea. In its current form, you really wouldn't know how to take the derivative using your basic chain rule or basic derivative rules. So I can take the ln of both sides of this expression. And now that I've taken the ln of both sides of this expression, this can drop down. And we have this. So now taking the derivative of this is much easier. So now I'm going to go ahead and take the derivative with respect to x. This is going to be 1 over y. And again, you have to tack on that dy dx. Now this is taking the right-hand side with respect to x. It's going to be first times the derivative of the second plus the second times the derivative of the first. So here I end up getting y prime equals y times 1 plus the ln of x. And we just discovered here above that y is equal to x to the power of x. So this is going to be x to the power of x times 1 plus the ln of x. So therefore, in this case here, y prime is x to the power of x times 1 plus the ln of x. And again, you can see a unanswerable question becomes answerable using logarithmic differentiation. Let's take a look at another. So in this one here, same idea. I'm going to go ahead and take the ln of both sides. So you get ln y is the ln of 1 minus 3x to the power of cos of x. So I get the ln of y is equal to, you can drop down that cos of x, and you get cos of x times ln of 1 minus 3x. And now again, take the derivative with respect to x here. I get 1 over xy prime, and then we got the first times the derivative of the second, and then plus the second term. And the derivative of cos is negative sine of x. So continuing this here, I end up getting here my y prime is y times minus 3 cos x over 1 minus 3x minus the sine of x ln of 1 minus 3x. And again, we can substitute in my y value, which is 1 minus 3x cos of x over minus 3 cos x 1 minus 3x minus the sine of x ln of 1 minus 3x. And then we've gone ahead and I've now taken my derivative. So this is y prime, be the following expression here. And again, becomes much easier and doable using logarithmic differentiation. Let's take a look at another example. Okay, so same idea here. We're going to go ahead and take the ln of both sides here. So I get ln of y is ln of e to the x to the power of 4. In which case I get the ln of y is x to the power of 4 ln of e. In which case I get ln of y is x to the power of 4, as the ln of e is 1. Taking the derivative of both sides with respect to x, you get 1 over y prime is 4x cubed. Y prime is y times 4x cubed, in which case y prime is going to be 4x cubed times that y value is x to the power of 4. And end up getting my answer here for y prime. All right, so there's a bunch of examples using logarithmic differentiation. Just take derivatives. You can also use logarithmic differentiation to prove the product rule. So let's go ahead and do that. You'll notice that what the product rule says is that if you have a function, let's say h of x is the product of two functions here, what the product rule says its derivative would be f at x times g prime at x plus g at x times f prime at x. So let's go ahead and prove this using logarithmic differentiation. So what I'm going to do here is I'm going to start off with this assumption that I have a function that's the product of two other functions, f and g. I'll take the ln of both sides. So this is going to be ln of h at x is going to be the ln of f at x times g at x, which case here this is the ln of h at x is the ln of f at x plus the ln of g at x. Now if I take my derivative, this is going to be 1 over h at x. So just like we've been doing in the examples, times h prime at x is going to equal 1 over f at x times f prime at x plus 1 over g at x times g prime at x. So therefore, h prime at x, which is what I want to find my h prime at x, is going to be h at x times f prime at x over f at x plus g prime at x over g at x. And getting a common denominator here, I get h prime at x is h at x, but I know what h at x is. It's the product of f and g, so I got f at x times g at x times f prime at x over f at x plus g prime at x over g at x. And we don't even have to get a common denominator here. I can go ahead and distribute this product into the fraction here, and I end up getting h prime at x is going to equal, you'll notice when I distribute this into my first term, the f at x will cancel, and I'll get exactly f prime at x, g at x. And likewise, when I distribute this into the second term, the g at x will cancel, and I get f at x times g prime at x. And that is exactly our product rule. The derivative of product two functions is going to be here. I've got it written the opposite way in my initial definition, but they're equivalent here. It's going to be equal to your first times derivative of the second plus your second times the derivative of the first, and you have your h prime at x. All right, that concludes today's lesson on logarithmic differentiation. Thank you.